So S will be big if you have lots of positive numbers, lots of positive paired differences, and those differences are big. So lots of positive differences. The more positive differences there are, the bigger S will be. And also, the positive differences are large in magnitude. Both those things, right? So if we go back to our previous slide here, right? If I had circled all 3 of these students, then I'd be adding more numbers. S would be bigger. But also, if this third student had a positive 4 instead of a negative 4, I would have included that 3, and that 3 is a nice big number, right? So the more positive differences there are, the bigger S will be, and the bigger the ranks of those positive differences, the bigger those positive differences are, the bigger S will be. In other words, the more big S is, the more we might actually believe that the pairs or the people within each pair, or in this case the seasons within each student, are different from each other. The bigger S, the more we might believe that the 2 groups we're comparing are different from each other. To complete this as a hypothesis test, we have to think about how to get the reference distribution. So I want you to think about this. So if our null hypothesis is that within each pair, the treatment has nothing to do with the outcome values, just as that was a null hypothesis for the sign test. Then when we think about different ways the data could have come out, we can think of flipping a coin for each pair to determine whether the difference turned out to be positive or negative. And actually, that's the way we're going to come up with our reference distribution. So if you think about our units here, 1, 2, and 3, right? It could be that all 3 of them have negative differences, which means that when we calculate S, we're going to get a 0. Or it could be that the first 2 have negative differences, and the third ranked one is positive, in which case we'll add up just the number 1. I'm sorry, just the number 3, and we'll get a 3. Or it could be that, let's see, the first one has a negative difference, second has a positive difference, third has a negative. And so the only rank we add is this number 2, et cetera, right? Until we think of, well, maybe all 3 of them will be positive. Then I'll take S equals 1 plus 2 plus 3, which is 6. And this column here consists of all the different possible values of S. It's all the different ways you can add up some of the numbers from 1, 2, and 3. You can add up just 1, just 2, just 3, or you can add up any 2 of the numbers. You can add up all 3 of the numbers, or you can add 0 of the numbers. That's what this is. And so here is the reference distribution: 0, 1, 2, 3, 4, 5, and 6. And if you actually finished this table, what you'd see is that there are 2 ways to get a 3, but each of these other numbers has only 1 way of occurring. Okay, that's the reference distribution under the null. Under the null hypothesis that the treatment groups have nothing to do with the outcomes, then this is the distribution that we'd expect to see for S. What do we do then to finish our test? We take the value of S we actually observed and we compare it to this reference distribution. So if we look back at the test we actually have here, right, we got S equals 3. Okay, so I'm going back. If S is equal to 3, that's the S we actually observed. You can't be more in the middle than that, right? So you can calculate a left-sided p-value and you get 5/8, or you can calculate a right-sided p-value, also get 5/8. You can calculate a two-sided p-value, it's actually bigger than 1 in this case. You can't get anything more expected than a 3. In other words, we do not have evidence based on this very small data set that fall is different from spring in an important way.